Hello again. So now we're going to do this problem. Catherine's time to run a mile follows a normal distribution with mean 345 seconds and standard deviation of 8 seconds. 85% of Catherine's running times are at least how many seconds? Now, I know what you're thinking. Okay. You're thinking, big deal, David. This is an easy problem. And it is. Not really, but it is. But what I want you to notice here is what it's asking, okay? So the first thing I'm going to do, as you might imagine, is I'm going to draw the distribution, okay? And I'm going to label it. So since it's running time, let's say it's t, and it's normally distributed with a mean of 345 seconds, okay? And a standard deviation of 8 seconds, okay? And the question is, well, and let's draw the figure, right? Okay. So we can know what we're talking about, okay? It's like this, okay? Well, let me make it a little lower for reasons that will become apparent soon. Okay. I want to draw my figure, okay? Like this. I know that the middle is at 345 because that's the mean of the normal distribution. And so now look at this, okay? Notice the way the question is being asked. 85% of Catherine's running times are at least how many seconds? So we're talking about 85% are bigger than some value, right? So in other words, let's say, so for example, we know that 50% are bigger than 345. So I have to go more this way to find that value, because if I go from here this way, it'll be already bigger than 0.5. So somewhere over here is the value of interest to us. Let's label that value as x, because it's an unknown to us. And what the problem tells us is that 85% is, we want to know what value that is, because that'll be the value that 85% of the values are bigger than or equal to that, right? So in other words, the area under the curve from right here this way will be 0.85. Okay? And because the area under the whole curve is 0.1, I mean not 1, is 1, that means that this piece from here to here, like basically forever this way, but I'm going to cut it off here, but really I mean to go forever this way, this area, the area of the tail, will be 0.15, okay? Okay? So in other words, we can say, that x will be the 15th percentile, because x is greater than or equal to 15% of the data points. And underneath here, we're going to use our standard normal. It's going to be 0, okay? Now, if the area to the left, if this area is 0.15, then we can already figure out what the standard normal value would be that would make that condition true. Okay? So what I'm going to look for, just to be clear, is I will find the value of z such that the probability that the standard normal value is less than that particular z we're going to find is equal to 0.15. Okay? So let's look at our standard normal table. Let's do that together here. Okay, so now here it's problematic. Okay, I want you to look at this with me here. It's in between here and here. Negative 1.4 and 1.3. You see? It's closer to this one, but it's roughly in between, and so we're going to estimate, okay? Okay. So let me make a note of that here. From the standard normal table, okay, we know that for the value z, the probability that the standard normal takes in a value less than that particular z for z negative 1.03, for negative 1.03, we have 0.1515. And for negative 1.04, we have 0.1492. We can see that 0.15 is roughly in between these. And so, as we did before, we're going to estimate this by taking the average. Okay? Okay. And what does that mean? That means that I'm going to average these z values. Okay? So, negative 1.03 plus negative 1.04, okay, divided by 2. That's going to be the z we're going to use. Okay, and that's going to be approximately 1.035. In other words, negative 1.035. Okay. For us, we're going to continue using the standard normal table because, again, I want to make sure that you guys know how to do that. But if we were able to use a calculator for this, or if we were to use technology, the actual value would be negative 1.03643338. Or in other words, this would be a better approximation if you use technology. Now, in any case, so now we know that this value of x, okay, that we want to find, which corresponds to the number of seconds, which is less than or equal to 85% of the running times of Katherine, that is going to have z-score negative 1.035, okay? And so we recall from the previous problem, we can use the z-score formula in reverse to get the value from the distribution of interest to us, okay? So let's do that together. And I'm going to derive that for you again here as an example again. So if I have z equals to x minus mu over sigma, what I do first is I multiply both sides by sigma. So that gives me sigma z is equal to x minus mu. I now need to move this mean to the other side. And I get that x is equal to sigma z plus mu. Okay? Like this. Look at that. That's perfect. Because now I have my sigma, 8, right? I have my z, this one. I have my mean, the 345. So my x, which is this value here, is equal to sigma, which is 8, times z, which is negative 1.035, right? And then plus my mean, which is 345. I can now plug this into my calculator, okay? So this is 336.72, okay? And so we're now in a position to state the answer to this problem. And what is that answer? Namely, 85% of Katherine's run times are at least 336.72 seconds. I hope you've enjoyed this problem and I look forward to seeing you again soon. Thank you so much.